Long short-term memory (LSTM) networks for forecasting. Long short-term memory (LSTM) networks are a type of recurrent neural network (RNN) designed to effectively learn and remember long-term dependencies in sequential data. LSTMs address the limitations of traditional RNNs, which struggle with long-term dependencies due to issues like vanishing and exploding gradients. Architecture of LSTM networks. LSTM cell structure. Here's a diagram representing the structure of an LSTM cell. LSTMs have a more complex architecture than standard RNNs. The key component of an LSTM is its memory cell, which maintains information over long periods. Each LSTM cell contains several gates that regulate the flow of information. Forget gate decides what information to discard from the cell state. This gate uses the sigmoid function to decide which parts of the cell state to forget. Input gate determines which new information to add to the cell state. It controls which values to update with new information. The sigmoid layer decides which values to update, and the tanh layer creates new candidate values to be added to the cell state. Cell state represents the memory of the network. The cell state is updated by combining the old cell state, scaled by the forget gate, and the new candidate values, scaled by the input gate. Output gate decides what information from the cell state to output. This gate determines the output of the LSTM cell. It first uses a sigmoid function to decide which parts of the cell state to output, then applies the tanh function to scale the cell state before multiplying by the output gate's result. These gates are controlled by sigmoid and tanh activation functions, which output values between 0 and 1 to modulate the information flow. Applications of LSTMs. LSTMs are widely used in various fields due to their ability to capture long-term dependencies. Natural language processing, NLP, for tasks like machine translation, text generation, and sentiment analysis. Time series prediction, used for forecasting stock prices, weather prediction, and anomaly detection. Speech recognition. LSTMs help in converting speech to text by maintaining the context over long audio sequences. In the context of operations and supply chain management, LSTM networks are particularly well suited for time series forecasting due to their ability to learn and retain dependencies over long sequences. Several companies across various industries have successfully implemented LSTM networks for forecasting purposes. Here are some real-world examples. Use case: demand forecasting and inventory management. Amazon employs LSTM models to predict product demand based on historical sales data, seasonal trends, and promotional activities. These predictions help optimize inventory levels across its vast network of warehouses, reducing stockouts and overstock situations. The accuracy of LSTM in capturing temporal patterns improves Amazon's ability to meet customer demand efficiently. Use case: cloud usage forecasting. Google Cloud uses LSTM networks to forecast resource usage and manage cloud infrastructure more efficiently. By predicting future demand for computing resources, Google can optimize server allocation and reduce operational costs. The LSTM models consider past usage patterns, workload seasonality, and other relevant factors. Use case: ride demand forecasting. Uber utilizes LSTM models to forecast ride demand in different geographical areas and at various times of the day. These predictions help in dynamically adjusting pricing, surge pricing, and ensuring an adequate supply of drivers. By accurately forecasting demand, Uber improves rider experience and driver satisfaction. Use case: content demand forecasting. Netflix uses LSTM networks to predict the demand for different types of content. By analyzing viewing patterns, user preferences, and seasonal trends, Netflix can make informed decisions about content acquisition and production. This helps optimize their content library and personalize recommendations for users. Use case: predictive maintenance. Siemens employs LSTM networks for predictive maintenance of industrial equipment. The models analyze sensor data from machinery to predict potential failures and maintenance needs. By forecasting equipment health and performance, Siemens can schedule maintenance proactively, reducing downtime and extending the lifespan of equipment. Use case: sales forecasting. JD.com, a major Chinese e-commerce company, uses LSTM models to forecast sales for various product categories. These forecasts inform inventory management and procurement strategies, ensuring that popular items are adequately stocked while minimizing excess inventory. The models consider factors like historical sales data, promotional events, and market trends. Use case: infrastructure capacity planning. Facebook uses LSTM networks to predict server loads and optimize the allocation of computational resources across its data centers. By forecasting demand for different services, Facebook can efficiently manage its infrastructure, ensuring high availability and performance while controlling costs. Use case: supply chain optimization. Walmart employs LSTM models for various aspects of supply chain optimization, including demand forecasting, inventory replenishment, and logistics planning. The models analyze vast amounts of data, including sales history, weather patterns, and economic indicators, to improve the accuracy of forecasts and enhance supply chain efficiency. Key benefits of using LSTM for forecasting: capturing long-term dependencies. LSTM networks excel at understanding long-term dependencies in time series data, making them ideal for forecasting tasks that require consideration of historical patterns. Handling nonlinear relationships. LSTMs can model complex nonlinear relationships in data, providing more accurate predictions compared to traditional statistical methods. Adaptability. LSTM models can be trained and fine-tuned to adapt to various forecasting needs across different industries and use cases. These examples illustrate the versatility and effectiveness of LSTM networks in forecasting applications across diverse industries, enabling companies to make data-driven decisions and optimize their operations. Handling computational complexity, data requirements, and interpretability. To handle computational complexity, it would be necessary to optimize the model architecture. Depending on the context, simple versions of LSTMs, for example vanilla LSTMs or gated recurrent units, might suffice, and they are less computationally intensive. One could start with few layers and then add complexity as needed. Dropout regularization can help in preventing overfitting, as well as computational load during training. The models used for LSTM can be compressed using techniques such as quantization, i.e., reducing the model's precision from floating points to fixed point representation, and pruning, i.e., removing connections in the network that are not significant. While reduction in complexity by optimizing model architecture and model compression will be helpful, it is still going to be important to deploy efficient hardware and software. For example, high-performance computing that utilize graphics processing units, GPUs, and tensor processing units, TPUs, and facilitate parallel processing. Firms can also take advantage of distributed computing frameworks, for example, Apache Spark or TensorFlow's distributed computing, that allows for models to be trained across multiple nodes. For managing data requirements, steps such as normalization of the data, using synthetic data to augment training set, integrating data from external sources that might be relevant for forecasting, using batch processing and mini-batch gradient descent, specifically to effectively deal with large datasets, and dimensionality reduction, for example using principal component analysis to reduce the number of features, can go a long way. To improve interpretability, one could implement attention mechanisms within the LSTM architecture to highlight which parts of the input sequence the model is focusing on during prediction, or could use saliency maps to visualize the importance of different input features and time steps in the prediction process. There are also some methods such as help in understanding of each feature to LSTM's prediction, for example Shapley additive explanation, and to explain individual predictions by approximating the LSTM model with a simpler interpretable model locally, for example, LIME, local interpretable model agnostic explanations. Sometimes it is also helpful to integrate multiple models, for example using LSTM plus decision trees or LSTM plus linear models, so as to have clarity on the predictions. As is always the case, proper documentation and reporting protocols can ensure that the knowledge gained by implementing these tools are preserved and enhanced as a company continues the journey of using these tools.